Talk about gravitation, orbits, and such. The learning goals for this is that I can explain what happens to the force of gravity between two objects when I change the mass, distance, and size of the bodies. That is all equation based, and I'll show you the equation. 2, I can calculate, that was weird. All right, 2, I can calculate, that was weird. My whiteboard went nuts. 2, I can calculate the force of gravity, the mass of an object, or the distance between two objects using Newton's universal law of gravitation. Once again, this is equation based. Now that I actually see that, it looks like the first one's not really equation based. This is just like kind of intuitive based on like the lab you did. Now, and we'll get there. I'll explain that in a minute. Number 3, I can explain what causes one body to orbit another. This is actually pretty cool. It's really all about circular motion. Watch this. Say I got a planet here. I'm doing bullet point 3. I can explain what causes a body to orbit another. Got a planet, big planet, right? Now let's say I got a little satellite here, right? Okay, well if the satellite was just sitting there, it would just fall, right? Because gravity is pointed down. The force due to gravity, which would be the centripetal force of this planet if it's actually orbiting, is straight down, right? However, satellites do not just sit in one spot. They have a velocity, a tangential velocity. It's going quite strong. Now, what happens if you've got a velocity already and then you start to accelerate? Well, you don't fall straight down with your acceleration. You actually turn, right? If you have an initial velocity and some force is applied at a right angle to it, you won't just go straight with the force. You will turn. So when the object starts to turn, look, and I didn't really draw my circle perfectly, but I'm not very good at circles, as you can tell. But look, you put that initial velocity and the force due to gravity together, look, the object just turns and turns and turns and turns and turns. And I can explain that another way here. Watch this. If I have a planet here and I fire a long-range cannon, and I fire it like this. I go, boo, right? There it is. I fired a cannon. What if I fire it farther, harder, more velocity? Boo! It lands there. More velocity. Boo! More velocity. By the way, I'm firing a cannon on a planet. Boo! More velocity. If I give it enough velocity, the velocity will make it so that the gravity of the planet can never catch up and it'll never fall. It'll orbit forever. This is the same as circular motion that you learned about in the last unit. Anyway, we'll talk more about that. If that doesn't quite make sense, that's okay. Probably doesn't make sense to most people quite yet. All right, this bullet point. I can explain what it means to be in a state of free fall. Great. We'll talk about that. And then this bullet point, I can calculate the acceleration due to gravity on an object in a given location. And we will get there. All right, moving on. You did this lab. I hope you're done at this point pretty much. You've probably figured out that you can change this force by changing the size of the planets or the distance between them, right? The distance between their middle points. That will also move the force. You probably figured out that if I change the distance between them, the force gets smaller. If I make the distance between them greater, the force gets smaller. There is sort of a inverse relationship. However, you probably figured it's not straight inverse. It's actually, if you did the math, it's actually a inverse square, but we'll get there. And then there is a direct relationship between the mass of the planets and the force between them. Or I call them planets. I know they're just weird balls being held by weird people. But here's the equation. Look, it turns out, yes, this is the mass of the two objects, mass 1 and mass 2. And there is a direct relationship between that and the force between them. Another thing to notice is that on this thing, there's two equal and opposite forces. What does that sound like? It sounds like force pairs. All forces come in pairs. Gravity is no different. The Earth is pulling on you, yes. Let's say that you have a weight. Let's say the Earth is pulling you with a weight of, let's say 150 pounds, right? Well, guess what? You are pulling back on the Earth with a force of 150 pounds. Okay, I know I'm not doing force in newtons here. I'm doing pounds because we're used to that. Okay, so you pull on the Earth pulls on you. It's a force pair. The reason that you don't pull the Earth up into the air is because you are way too small to do that. All right. What the heck? And then, okay, we got this radius squared. So the radius is the most important factor here. The distance between the center of mass of the two objects. It's squared, and so it affects it much more than the masses do. All right. Big G, the universal gravity constant. This has been determined with calculations based on objects in space and such. It's determined that basically, okay, you take the mass of the two objects, you divide it by the radius squared. It doesn't quite equal the force. In order to get it to equal the force, you always have to multiply it by this constant called big G. A constant means this number is never going to change. This unit is very weird, but guess what? It's going to make the units balance out for us, and I will show you what I mean by that in a minute. Practice. All right, calculate the force of attraction between two billiard balls, and they are 0.3 kilograms each, and they are 0.75 meters apart. One thing I want you to do is keep in mind that 0.75 meters apart, that is the distance between the center of mass of the billiard balls. Okay? I want you to try this on your own. The Edpuzzle is going to pause so that you can try it on your own. Get to any answer you can, type it in. I'm not concerned about you getting to the right answer, but I am concerned about you actually trying, because actually trying makes you actually learn. Give it a shot. I'll see you in a minute. All right, welcome back. So you've tried that problem, and you'll find it was pretty straightforward. I think the only thing that it might become an issue is getting ourselves to put in the scientific notation correctly with big G. That can be an issue, I know. All right, calculate the force between the bowling balls. Okay, so force due to gravity between the billiard balls. You might be thinking, there is no force due to gravity between billiard balls. I would argue, no, there's actually a force due to gravity between all objects that have mass. But if you said there was zero force, you're not entirely wrong, because you could just round down to zero, because it's going to be a very small force, I bet. But let's check it out. All right, force due to gravity equals. That's stupid. I should list my variables before I do this. My variables are mass 1, 0.3 kilograms. Mass 2, I'm going to remember that it's 3 sig figs. I'm not going to write them all out. 0.3 kilograms. That's supposed to be a 3. I know big G. It's right here. It's already given. The radius, the distance between the center of mass is 0.75 meters. I have everything I need now. Force due to gravity equals all this, right? So I'm not going to redraw that equation. I'm just going to plug things in. Big G is 6.673 times 10 to the negative 11 Newton meters squared divided by kilograms squared. Y'all don't have to do all of this dimensional analysis stuff. I want to do it to show you that you're going to end up getting newtons, right? Because you're solving for a force, you should get a force unit. I want to show you that it works out. You can just trust that you're solving for a force, you get there. All right, times what? The two masses, 0.3 kilograms. And I'm just going to say squared, because it's, right, I'm going to have mass 1 times mass 2, and they're both 0.3. So that's the same as 0.3 squared. Divided by the radius squared, 0.75 meters squared. Look what happens here, folks. Kilograms squared divided by kilograms squared. That's going to cancel out. Meters squared divided by meters squared. I'm going to be left with newtons in the end. So I am solving for a force. I'm left with newtons, and I'm set. All right, moving on. 6.673. Second, double E, negative 11. You got to do your sig figs. You got to do your scientific notation right. Times 0.3 squared. Divided by 0.75 squared. So my force due to gravity is teeny tiny. I get 1.067. So I'll just say 7. 1.07 times 10 to the negative 11 newtons. So basically 0. But there is a force. There's a force between anything with masses. No matter the distance. Just if the distance is real far, it's basically 0. And if the masses are real small, it's basically 0 as well. There's the number you should have gotten. I hope you got there. If you didn't, try to figure out what went wrong. All right. Next one. A gravitational force between two people is 7.5 times 10 to the negative n. So what is that? Gravitational force. Oh, you know what? Hold on. I want you to try this one on your own as well. All right. And then the Ed puzzle is going to pause and let you do that. Okay. Welcome back. The gravitational force between them is 7.50 times 10 to the negative 8 newtons. If they are meters apart, we're going to go with that's radius. It should say their center of masses is 2.75 meters apart, but I think that was implied. And one person, we'll call that mass 1, equals 85 kilograms. Mass 2 equals question mark. I don't know that one. So first, if I'm going to take this equation, force due to gravity equals G m1 m2 divided by radius 2. I got to solve for m2. Okay, so if I'm going to solve for m2, I'm going to first multiply by radius squared. That cancels out there. Then I'm going to divide by G m1 on both sides. And I'm left with m2 is equal to the force due to gravity times the radius squared divided by big G times m1. That is, I'm just going to plug all those numbers in because I already have them listed out. 7.5 times 10 to the negative 8 times the radius squared, 2.75 squared, divided by, I'm going to put this all in parentheses, divided by big G, which is 6.673, second double E, negative 11. Now I put a parentheses in my denominator so I can hit times here. If you didn't put a parentheses, you'll have to divide it by again. Divided by mass 1, which is 85. I get 99.99. This dude weighs 100 kilograms. There you go. Now, if you do all the numbers, you'll find that it all works out. I know that I'm solving for a mass, so I'm just going to put kilograms in and move on. Okay, good job. All right, check this one out. Since weight comes from gravity, right, so mg, mass times the acceleration due to gravity, it equals the force. And we know that force equals this equation. We just had that equation, so we know that's true. Well, that means that, and keep in mind, this mass times acceleration due to gravity, that's the mass of an object, not the planet being accelerated, right? That's the mass of an object. So, like, if you want to know the force due to gravity acting on a thing, it's mass times little g, the acceleration due to gravity, right? So that means this is the thing, right? So this thing is going to get canceled out. So that basically this is saying big G times the mass of the planet times the mass of the thing. Well, if that equals mass of the thing times little g, guess what? Mass of the thing cancels out. I'm left with little g, the acceleration due to gravity, equals big G, the gravitational constant, times the mass of the planet. Or that's kind of not very, I don't like that. This is, maybe we'll call it the central object. Because there will be sometimes you might be figuring out the acceleration due to gravity on Earth due to the sun. And so you don't want to have planet written there because what's the central object? It's the sun in this case, not a planet, right? And so it's more specific. So M1, when something cancels out, the thing that cancels out is whatever is doing the orbiting, okay, not what is being orbited around, if that makes sense. So I'm going to say that the central object stays there. So that's the important thing about this equation. The most common thing students get wrong here is they say, oh my gosh, there's only one mass. That must be the mass of the thing that I'm interested in. No, not necessarily. It's probably the mass of the planet. It's the mass of the central object, whatever the thing is orbiting around. Okay, so that's important. All right, so find the value of G on Earth using Earth's mass, Earth's radius, and You know it's 9.83. I'm going to ask you to try this on your own. Try to get yourself to 9.83 because you know, well, it's like 9.8 is what we use, but whatever. Yeah, so this is the number you'll end up getting, and we use 9.80, but that's because, you know, something is rounded a little too much. But honestly, I'm not going to do this, guys, because you can do this. This is big G. M1 is the mass of the Earth. Radius is there. And just make sure you can get it right, and you're fine. I'm going to move on for the sake of time because this video is already getting a little bit long. For this, I want to rank in order from largest to smallest the free fall acceleration on the surfaces on the following planets. Okay, folks, this is a great question. I've got the masses. Okay, so I know, I know that mass is going to be important, right? Mass is going to be directly proportional to acceleration. This little g is acceleration due to gravity. Mass is directly proportional to it. So the ones with more mass are going to be there's going to be a bigger acceleration, right? I also know that the square of the radius, the inverse square of the radius. So acceleration due to gravity is directly proportional to the inverse radius squared. So that means the bigger the radius, the less acceleration due to gravity I'm going to have, which makes sense, right? There's going to be less force acting on an object if it's farther away, right? And so that means these bigger ones are actually going to end up, because they're bigger in radius, but they're not necessarily bigger in mass. Well, this one is, but so these smaller ones are going to end up having more acceleration due to gravity because the radius between the object on the surface and the center is smaller. So it looks like this 2m, that's going to be our biggest. That's our largest. And then this, what's more important? This mass or the fact the radius is smaller? Guess what? The radius is squared, so the radius being smaller is more important. And then our 2 mass one is the next largest acceleration due to gravity. And then the one that is really big but really light is the smallest acceleration due to gravity. What this means is these giant planets in our solar system, these gas giants, Jupiter and Saturn and these big old gas giants, they're really big, but they're like made mostly of gas. And so actually their gravity might be smaller than you might think. And then what is a C? C would be here. Okay, here's this last one. So when gravity is the cause of centripetal force, that's whenever something's in an orbit. Okay? So when something's in orbit, you can calculate the tangential velocity. The same thing happens, right? Remember that the force of the centripetal force is actually just mass times velocity squared over radius. Remember that from our last discussion. Well, that means that this, and the mass is the mass of the object, not the mass of the central planet or whatever. It's the mass of the thing that is in motion, if you will. And I know motion is relative, but when we think about an orbit, the thing in motion is usually the satellite or the moon or whatever, right? So this is the mass of the object. So guess what? This is the mass of the planet or the central object. This is the mass of the thing in orbit. And then these masses are the same, and they are going to cancel out. So if you're going to find the orbital velocity of something, it's going to be big G, which remember is that constant number, which was actually, I'm going to need big G. I'm going to need it, so let me grab it real quick. Yeah, that's fine. Why is this? Whatever. I'm grabbing a circle with big G. I don't know why, but I am. So remember that big G is that number. And then times the mass of the central mass. So that's usually a planet. It could be a sun, whatever, but it's the thing that everything's orbiting around, right? Divided by the radius, which is the distance between the object and the planet and the radius of the planet as well. Keep that in mind. So The International Space Station is orbits at an altitude of 400 meters and has the approximate mass. It's really pretty big, actually. And the Earth's rate, or pretty massive, I should say. And the Earth's radius is such. Calculate the tangential velocity. So what does that mean? All right, well, I feel like this video is too long. So I'm going to ask you guys to solve it. Well, no, I'll solve it. I need to, yes, it'd be kind of. So here's the radius of Earth. 6.37 times 10 to the 6 meters. And then the space station this is not to scale, is 400 meters up. That can't be right. 400 meters, that's it? That doesn't seem like a lot. 400 meters. Well, this is the last side of the video. That seems like not very high to me, but maybe. That doesn't seem high enough to me. Does that mean it's supposed to be kilometers? Let's go with let me just real quick. This doesn't seem right. Altitude of the space station.
The altitude of the International Space
254 miles to kilometers.
254 miles is 408.773 kilometers.
This should say kilometers. And so what that's going to be is 400,000 meters. Sorry about that, folks. We'll do this together. I won't make it a question you have to do on the dead puzzle because that's going to take you too much time for this video. But I actually recommend you pause it and try it on your own. Always learn better doing that way. All right, so that's 400,000 meters. That makes more sense. Okay. So the radius between the center of the Earth and the actual satellite is 6.37 times 10 to the 6 meters plus 400,000 meters. Okay, that's an important thing to know. 6.37 times 10 to the 6 plus 400,000 meters. So the radius between these two objects is 677,000,000. 6 million meters or so. All right. And honestly, at this point, what's the velocity? Like, just plug it into the equation now, right? We got a radius. We got the mass of the Earth. This mass doesn't matter. So that means, what is the mass of the Earth? We don't have the mass of the Earth. Ooh, what a jerk. What a jerk move. We've got it over here. The mass of the Earth is 5.98 times 10 to the 24 kilograms. All right. 5.98 times 10 to the what? 10 to the 24 kilograms. I'm kind of interested now in knowing, so I'm going to solve it. All right, let's check it out. Velocity equals the square root of big G times the mass over radius. And that is the square root of the big G, 6.673 times 10 to the negative 11. And I'm not going to save the units for another day. Times the mass of the Earth, which is 5.98 times 10 to the 24 kilograms, all divided by the radius between them, which is this huge number, 6,770,123 meters. So I'll put that in. Let's figure out how fast that space station is going. 673 times 10 to the negative 11 times 5.98 times 10 to the, seriously? That's heavy. 24. It's the Earth, though. Divided by 6,770,000. The velocity is 9.8 370,073 meters per second. Real fast. That is real fast. Somebody check that up on Google and see if I'm right, because that's a number that we can figure out if I'm actually right or wrong, if I did my math right. All right. That was plenty of time, I think, for us. Thank you for watching. Please, as always, let me know if you have any questions by putting something on the message board or sending me a message. Talk to you soon.